Netware. In the 1980s and early 90s, netware occupied a large percentage of the networks in existence. It exists as a network operating system that can run on most media access control protocols and deliver data integrity in a reliable manner. In this nugget, we're going to start off by looking at the netware history, and then we will take a detailed look at the protocol model, followed by a discussion on the IPX addressing schemes and its routing capabilities. In the last two sections, we're going to clear up some confusion on the encapsulation naming conventions, and we're also going to take a look at the service advertisement protocol process. The history of netware can be traced back to a company known as Novell Incorporated. And in fact, Novell developed netware in the 1980s, which explains why their heyday was the 1980s and early into the 1990s. In fact, they would have kept on their quest of rule of the world, if you will, if it wasn't for Microsoft coming out with their network operating system. It was based on the TCP/IP protocol. This was their first real competition, and in my eyes, I feel that Microsoft is leading in that game at this point. So let's define what network operating systems are. All right, the first thing, a definition might be distributed file and application system. Now, the key word there is distributed. In the old days, you would have a client here, and on this PC, you had to have every application resident that client might want to use, okay? This could get costly if you had a number of clients that needed the same application. Now you have 1, 2, 3, 4, 5 instances of that same application having to reside on different hosts, okay? So this distributed idea came into effect by placing that same application on a server and saying each of these clients now can have access into this server to that application. Makes administration much easier because now you can administer the one application on a server. For upgrades and things of that sort, it's much easier rather than visiting 5 different computers. And this is on a small scale. You can imagine on a true large-scale environment how much time that would save. As I had mentioned earlier, Microsoft has a network operating system as well, but there are others out there that you might be familiar with and will help you understand exactly what we're talking about when we say that netware is a NOS. And some of those are NFS, which is the Network File System. This was introduced by Sun. We also have Vines. Vines is a network operating system that was introduced by the company named Banyan. They had Street Talk as well, if you recall. All right, so going back to netware, it got derived, or it was developed out of the idea of XNS. This was a common networking protocol at the time, and it stands for Xerox Network System. Although comparison to these other network operating systems will give you a decent idea of what netware can or might do, the best way to get a good idea is to look at its protocol model, and that's what we have here. This is the netware protocol model, and we start from the bottom and work our way up in the comparison to the OSI model that we have here. So just a recap really quick, the physical, data link, network, transport, session, presentation, and application layers are the 7 layers of the OSI model, and they map directly across in this manner to the netware model. So let's start at the top. These first 5 layers are netware specific. In other words, Novell wrote code and designed the network operating system within these 5 layers. The bottom 2 layers were going to be used with existing media access protocols. In other words, these are not netware specific. So the design concept here was, instead of sticking to a proprietary media access protocol, netware would be able to ride most, if not all, existing media access protocols, and in any that were to come in the future. So let's start working our way up from this level here, the specifics to netware. All right, what we have is the IPX protocol, stands for Inter-Network Packet Exchange. This is the equivalent to IP in the TCP/IP model. And just like IP, it's connectionless. So what does that mean? It means that it has no formal handshake with the destination saying that I will guarantee delivery of these packets. I'm going to put it out there, best effort on the wire, and let it ride. It is also responsible for logical addressing at this layer and end-to-end packet delivery. The reason that the network layer is able to define itself as a connectionless protocol is that up in the transport layer here exists a connection-oriented protocol, and they can just bump that responsibility up to that level. So as we're talking about that, we're talking about SPX, which is Sequenced Packet Exchange. Now the sequence gives you a hint into the fact that it is connection-oriented, and as packets go across that network, we're going to keep track of the sequence so that we can get acknowledgments back to say that, yes, I received the last packets that you had sent. This is where you're going to notice a big difference between the network model and the TCP/IP model. At the transport layer, TCP/IP defines a protocol for connection-oriented and also a protocol for connectionless. In this aspect, network does not. In fact, what it says is these upper layer application, presentation, and session protocols can speak directly to IPX. I guess the thought there is, why interject another protocol when all I'm going to do is deliver a connectionless environment just as I am with IPX? All right, and then as we move up, we have the Service Advertisement Protocol. It spans, as you can see here, application, presentation, session, transport, and half of network. SAPs are unique to netware, and that service advertisement that it speaks of will advertise not only the addresses associated with a specific device, but it will also advertise the service that that device offers. So as you can tell, this is probably, and it is, dedicated to server applications, servers and routers. And as you can see, the model also supports other application protocols like the Network Core Protocol and Network Shell protocols. Moving back for a second to the network layer or the IPX environment, I want to discuss routing for a minute because this is where routing will exist just as it does in the TCP/IP model. And in fact, you are going to support at this level static routing or dynamic routing. Remember that static routing is a manual routing that you will define, and so it can get cumbersome in large networks. But beyond the static routing, dynamic routing that is supported, if you're looking for distance vector, RIP is supported. If you're looking for a true link state protocol, they have NLSP. And then if you're looking for, again, that balanced hybrid, just as we saw on the TCP/IP model, we have EIGRP support as well. Each of these routing protocols will be discussed in more detail in the routing section of this nugget. Before we move on to addressing, I want you to take note that, again, these lower two layers, the data link and the physical layer, are not network specific. What does that mean to us? When we say that we're going to take care of addressing at the IPX layer, it's not only the logical addressing, but it also has to be the physical addressing, because we don't have a network specific data link layer where we would normally take care of physical addressing for the network operation or the protocol that's operating as a NOS. So we're going to combine the two. Let's look now at addressing. And when we combine the two, we're going to call it IPX network address. All right? And it is a combination of the network number and the network ID just divided by a period. Let's talk more specifically about what the job of a network address is. It has to be unique in its environment. And we're not talking about a subnetted environment like we would have in TCP/IP, because indeed subnets don't exist here. It has to be unique within the whole network environment. Other characteristics of the IPX network address are that it has 80 bits associated with it. Now these 80 bits are represented in hexadecimal. Keep in mind that hexadecimal is a base 16 number system that is written with characters that represent the values 0 through 15. These are decimal values here. Now they are represented in hexadecimal with characters 0 or numbers 0 through 9 as they're capable, and then at the point that we go into double digit numbers, they're represented by letters. So that would be A, B, C, D, E, and F, because A represents 10, B 11, C 12, D 13, E 14, and F 15. So the result of 80 bits being represented in hexadecimal is going to be a string of 20 characters, 20 hexadecimal characters, okay? Now, when we say that it's made up of a network number and a network ID, let's break down each one. We're going to start with the network number. Here we're going to represent 32 bits. Now keep in mind, these 32 bits that were allowed for a network number in netware correlates to the 32 bits that were allowed in the TCP/IP environment as well for a subnet. In fact, if I draw my router here, in many cases, I'm going to have IP and IPX operating in the same environment, in other words, on this interface. Now, I'm allowed a 32-bit address written in dotted decimal notation for IP. So what is normally done or commonly accepted is to write these same values in hexadecimal format so that I can have an ID for my network number. Let me show you below an example of how this number can be represented to be the equivalent, or the hexadecimal equivalent, to this dotted decimal notation. The first thing we're going to have to do is take these decimal values and convert them to binary. The 192 converts into 1, 1, followed by 6 zeros, 1, 2, 3, 4, 5, 6. And then we have the value of 168, which is going to convert into 10, 10, 10, 0, 0. The value of 2 is pretty easy. 1, 2, 3, 4, 5, 6 zeros, a 1, and a 0. And then obviously in this last octet, we have a decimal value of 0, so that's going to result in 8 consecutive zeros in that octet. Now what we're going to do is, I've written the numbers here simply to give you the correlation back to this dotted decimal notation. But when we convert this into hexadecimal, we're going to lose the dots, okay? So let's see what this is going to result in. What we do is we take groups of 4 binary place values, and that's going to represent 1 hexadecimal character. Let me explain why. Remember the values, 1, 2, 4, and 8. This gives you the possibility of representing decimal between 0 and 15, which is exactly what we said we're going to do up here with our hexadecimal values. So 4 binary units are going to result in 1 hexadecimal character. Let's start figuring this out. We've got 0 here across the board, so 0. Same thing here. All right, here, dividing this by 4, we come up with a 2. The reason for that, again, the placeholders. 1, 2, the 2 places on. A 0 here. Here, dividing it into groups of 4, we have a value of 8, because 1, 2, 4, the 8th place is on. Here we're going to have the 2th place and the 8th place on, which is a result of decimal 10. Looking at our chart, after 9 we go into the characters because we can't represent 10 with a single digit. So this is going to result into the hexadecimal character of A. All right, keep it on. The 4 here is going to result in the 0. And then now I have 1, 2, the 4th place is on, and the 8th place results in 12. So I have 10, 11, 12. We're going to represent this with a C character for hexadecimal. So the resulting network number is going to be C0 alpha 8 0 2 0 0, followed by a period, and then we move into the network ID. This is going to be a representation of 48 bits. And that is not by mistake. You got to understand that that 48 bits is exactly the number of bits that are associated with a physical address or a MAC address. Remember, when we have a device, it can be a PC with one interface. That network interface card has a physical address associated with it. The same thing for routers. Each interface is going to have a physical address associated with it as well. So what Novell did is they said, you know what? Already, by definition, those addresses have to be unique. They have to be 48 bits long. They accomplish what we want to accomplish, so why don't we just use that as the network ID portion of our address, which will give you this last 48 bits. That physical address is represented in groups of 4 characters divided by periods. And so we're going to see here 000.0C9288 Fox or F Bravo. This is going to be the MAC address that we found on this router interface, and this is the network number that we assigned. Together, they're going to be the IPX network address. Okay, one's a number, one's an ID. Now, because these are represented together, that gives us half of the reason that in a netware environment, we don't need to run address resolution protocol. If you recall, that's one host sending out a broadcast onto the wire saying, I have an IP address or a logical address, the layer 3 address, and I want to know the layer 2 address. Can somebody answer if that's your layer 3 address? And then you find one person that received the broadcast that says, hey, that's my IP address. Let me go ahead and supply my logical or my physical address back to the person that asked the question. Now that we understand the netware addressing scheme, we can take those addresses and apply them to interfaces so that we can bring our netware network up, or our IPX network. What we're going to see here is a series of commands to do that. First of all, let me get you familiar with our prompt. We have the host name here, whatever the host name of your router is. In the case of this router, it would be R1. Then we have the configuration prompt, letting you know you're in configure via terminal. And in here, we're going to have our command, IPX space routing. This is a global command to turn on the ability to have IPX run on individual interfaces. Without this command, you can't do it. If you try to enter this command without entering the global IPX command, it'll simply give you an output saying, can't do it. You got to go back and issue the command IPX routing. Here we have an optional piece of this command. And it asks you if you want to input the IPX address. Now this is the router asking you the question of the IPX address. It's somewhat misleading in the label. Really what this is a node ID. What the router is going to do is it's going to take the first MAC address from either an Ethernet, a token ring, or an FDDI port and assign that MAC address as the node ID. If you don't assign an IPX address here. And in fact, I wouldn't do it. But if you want to, or there's some special circumstance that you need to, you can manually assign that address. All right, then we get into an interface. Interface serial 0 in the case of our diagram here. We have router 1. Serial 0 has a link running over to router number 2 and its interface serial 0. We want to activate IPX on this network, and we want to give it a network number of ACE1. Remember, this is a hexadecimal value, okay? It's not a word, it's not ACE1, it's a hexadecimal value, all right? And what we do here is type in the command IPSX space network space the network number, that's where we supply this value, and then we have the ability to put in a specific type of encapsulation. Remember that we talked earlier about all the media access protocols that can be supported by IPX. This simply lets you choose from all of those available. You don't have to, though. It will go with the default, and this link will be up and running with an IPX network and ready for testing. The next step is to jump into our routers and make this happen. We're going to start out with router number 1. You can see that I'm already in the configuration mode, so I'm going to type in the global command to activate IPX routing. All right, I'm going to hit the question mark at the end of this part here so that I can show you that indeed it does ask for the IPX address of this router. Again, that's the manual input of the node ID. We're not going to do that here, so let's hit enter. And now we have it set up globally. Now we have to get into an interface. We'll opt for serial 0 and set up the IPX network number. So IPX network. The network number is going to be ACE1. And then if we wanted to, optionally, we can opt for encapsulation. So encap space question mark is going to show me the options that I have here. We're going to go over these in more detail later in this nugget, but for now, I just want you to see that they are there. So let me space back over the encapsulation option and hit enter. Now we have IPX network number ACE1 set up on the interface on router number 1. Just as was the case in IP, we have the same case with IPX. This interface is configured. This one is not. Traffic will not connect across this. So we have to go over to router 2 now and do the exact same thing that we did on router 1. So let's go in there and put in IPX routing, just the basic command, get into an interface, interface serial 0, and then activate IPX network ACE1. It's going to be the same network identifier. This is true as it was in TCP/IP. Whatever that subnet address was, we had existing on both interfaces. The same thing here. This hexadecimal ID has to exist everywhere that we have a broadcast domain or this local area network or wide area network connection. All right, so let's hit enter here, and now we should be configured. Let's test that out. We have the capability to ping with IPX. It's part of the extended ping functionality. So if I type in the word ping here and then hit enter, where normally I would put an IP address, it's going to ask me which protocol would you like. I'm going to opt for IPX. Okay, then it's going to ask me a target address. What I need to do is go down into router number 1, bring it up, and I need to do, first I need to get out of the configuration mode, but put in show IPX interface command. And once I do that, what I'm going to see, as soon as I scroll up a little bit, is the IPX address right here. This is the whole address. Remember, it's got the network number, the ACE1, coupled with the node ID. So I'm going to take this, copy it, come back to router number 2, paste it into this field as far as the target IPX address, hit enter, go with the defaults from this point on, and there you have it. You see success rate is 100%. I'm able to ping the distant end. So what we did there, let me show you, is we started at router 1, send out Novell or netware packets across to router 2 and had a response to those packets to verify connectivity. Before we leave this section on addressing, I want to give you one more show command that we can use so that we can discover how IPX is working on our network. Let me get rid of that last show IPX interface command, and what I'm going to illustrate here is the show IPX traffic. It's going to give us quite a bit of information, so let me blow up our window to its maximum, and here we go. We see the command show IPX traffic. What it's going to give you is packets that are received. It's also going to give you broadcast information. Here that we see that we sent 4 broadcasts. We see packets that were sent. We had 5 generated, 4 had encapsulation failed, and it gives you these types of error statistics. And then it gives you statistics pertinent to specific applications or routing protocols. Here we have SAP counters. Here we have RIP counters. We also have echo counters. These were the 5 echoes that we sent out. So we received 5 echo requests, and we sent out 5 replies from this router, because this is the router that was being pinged. And then we have watchdog, and the last couple of entries we're going to have EIGRP, Q-links, and the trace. I just want you to know that all that information is available under the show IPX traffic command. So far in this nugget, we've covered the history of netware. We've also looked at the model involved with the protocol netware, and then we looked at addressing. Now we're going to move into routing and an understanding of how routing is affected in the netware environment. I'm going to start off by showing you the protocol model first so that you can see, again, that routing takes place here in the IPX layer. We have RIP, which is our distance vector protocol. We have NLSP, which is our link state protocol, which stands for netware link state protocol. Pretty easy, right? And then we also have EIGRP, which, as you know, is Cisco proprietary, but it's advertised as a balanced hybrid protocol. In other words, the best of both worlds. So let's go over these a little bit. We'll start with the EIGRP. Like we said, balanced hybrid, it has a composite metric. Instead of just having a simple metric like RIP, it has a composite metric. It's similar to that you will see in NLSP, but at the same time it has faster convergence and less overhead. All right, moving on to NLSP. It's a true link state protocol, and it's based on the open shortest path algorithm. It more closely resembles ISIS, which is another link state routing protocol, than it does any other. Then we're going to move into RIP, which is the distance vector protocol. We're going to cover this a little more in depth, and the reason for that is, as soon as you type in the command that activates IPX globally, which as you recall will be IPX routing, it is going to enable RIP routing for IPX automatically. And you're going to see that in the next lab scenario that we're going to work at. So because it's automatically turned on, let's talk about it. Let's talk about its similarities in the IP RIP world. And the first is its distance vector routing protocol. It has periodic updates, which means that router is going to send its update or its route table every n number of seconds. In this case, 60 seconds. It also has a max hop of 16, which means you can't go further than 16 hops across a router. Of course, it's implemented a bit differently here, and when we get into the packet structure of an IPX packet, you're going to see how that happens. All right, other than that, let's talk about the differences now between the IPX RIP and the IP RIP. First of all, the preferred metric with IPX RIP is called a tick, and it's a measurement of delay rather than the hop count like you would normally have with IP RIP. Now, IPX RIP will support hop count, but it does it as a last resort. If I have a tie in ticks or delay, then it's going to use hop count as a tiebreaker. All right, what else do we have here? IPX RIP and IP RIP are not compatible. They will not work together, and it's mainly because of this type of metric that they're using to measure. Let me give you the scenario that we're going to use so that I can demonstrate to you that the RIP IPX protocol is automatically started. What we have here is our lab environment. We've already set up between router number 1 and router number 2, which exists up here, this link with a network number of ACE1. This is what we did in our last exercise. Now what we're going to do is set up ACE2 and then ACE3, first on this serial link and then on this Ethernet link. And it's going to give us this triangle effect of 3 routers running IPX networks between each other. Now I have the same diagram on both levels of this whiteboard, and the reason for that is I want you to be able to reference this whiteboard as we're doing our configuration on each router. And since I do have those layered, we're going to be able to see it each time. Before we leave this area, let me label our routers. This is router number 1, router number 2, and router number 3. For this first leg of our connectivity, we're going to establish ACE2 as an IPX network number between router number 2 and router number 3. All right, router number 2, we have it ready in configuration mode. The first thing we're going to do is get into an interface and configure this IPX network number. The reason we can do that is you got to remember, we already have IPX routing set up globally because I have this link up and running from router 2 to router 1. You only set that command up one time, and then you can get into as many interfaces at that point as you need to. So let's make that happen. Interface, serial 1, and then we're going to opt for IPX network, and the network number in this case is going to be ACE2. Hit enter, and we're set to go on router number 2. Let's close that up now, and let's look. on router number 3 for our configuration. In this specific instance, we have not set up the IPX routing command because we don't have any IPX links up yet. So we do need to take that step this time. IPX and then routing, enter. Then get into a specific interface. Interface, serial, 0/0. Now that we're in there, let's get rid of all these informational type lines. We can activate IPX network, and the network number is again going to be ACE2. All right, at this point, we should be up and running, and what we're going to do to verify that is run our ping again. It's ping, enter, then it's going to ask you the protocol, IPX, and then we need the target address again, which is going to require a visit to router number 2. Let's get out of the configuration mode. Let's do show IPX interface, and we're going to opt for a specific interface this time. This time it's going to be serial 1, because otherwise it's going to give us every interface on this router. When we do that, again, all of the information is going to scroll across. Let's go ahead and come back up, and we're going to copy that address. Copy it here, come up to this router, use our paste command, and we're ready to go. We're going to accept the defaults from there. And there you have it. We have 100% success rate in pinging across the network that we've just established between R2 and R3 for ACE2. At this point, I have 2 of my 3 IPX networks up, ACE1 and ACE2. Okay, so what you need to be aware of is, as I pull up an IPX route table for this specific router, which I do with the show IPX route command. So it's similar, obviously, to the show IP route, except for in this instance, we're looking for the netware information or IPX information. When I type this in, it is a given that I will have information on directly connected networks. So router 3 here should have a knowledge of ACE2 as a network, right? Existing connected. But it should not have any knowledge of ACE1 if we don't have any routing protocols running. Now let's test that theory out and see if that's exactly what happens, because as we said earlier, RIP comes up automatically. And because of that, show IPX route. Because of that, we're going to see RIP entries. Let me make this a little larger. All right, we have the first entry for ACE2, which is this network here, directly connected to router 3, and it even tells you that. That C indicates that it's a connected network. But then we have an entry that starts with R, which indicates we learned this via RIP. And it's saying that the network ACE1, which is this network here, exists via ACE2 and then this node ID. Together, this is a network address, and it's the network address right here for this interface on this router. So it's telling you, if you want to get to this network, IPX network, then you need to go through router 2 to get there. Let's check our results on router 1 as well. This is no longer router 2. Look at the prompt, it's router 1. All right, what we're going to do is the same command, show IPX route. And we should have learned via RIP a route over to ACE2, which we did here because it's not directly connected. Bringing down this router interface, here we can see that. Router 1 has no connectivity to ACE2, but I do say that it's reachable via a RIP update across ACE1 and then this node ID, which is the interface right here. Continuing with our configuration, we're going to set up the network number for IPX ACE3 here on this Ethernet link between router 1 and router 3. Here I have the router 1, so I'm going to go ahead and conf-T, get into the interface, E0, and at that point, IPX network, and it's going to be ACE3 this time. All right, that's good to go. Close that up. Let's go into the other router for the other side, and we are going to get into interface. Oh, sorry, configuration mode first. Conf-T, interface, E1/0, and then IPX network, ACE3 is going to be set up. Get out of that mode, and now we're going to run our test as we did before. We're going to ping. I got broken up a little bit there. The protocol is going to be IPX, and let's run down to the other router, and we can pull our information for our addressing. Show IPX interface, and in this case, we want E0. All right, scroll up a bit. There it is. We'll copy it here without the comma. Take care there. And then come up, paste it there, hit the defaults from there on out, and there you go, 100% success. With that action, we've completed this scenario, and now we have all three of our network numbers for IPX set up and running. Next, we're going to move into looking at the packet structure for IPX. And the reason we're doing this is because you got to recall in the model, we don't have a layer 2 specific outline for netware. So what we're going to have to do is carry the information or the addresses for that layer in our IPX packet. So I just want to make sure you see that and some other interesting things about it. We're going to start off with this checksum. This thing is 2 bytes long, and it's a waste of 2 bytes because it's not used. It's simply going to be 4 Fs in a row representing those 2 bytes. Then we're going to have packet length. Obviously, this is self-explanatory. It's the length of the packet, but what you do need to know is that it's measured in bytes. Then we're going to have transport control. This is actually pretty cool. What it does is it counts the number of routers that you hop through. So let's say I have a node here, and I have a router, and a router in the environment. As I'm sending this IPX packet through these networks, at this third area here, this is going to have a counter of 3. Now the reason for this is if this counter ever reaches 16, the packet is discarded. So it's a way of keeping like a count to infinity from happening like you do in other protocols, but it actually happens within the packet structure. So if this hits 16, in other words, if it's traversed 16 routers, it's going to kill itself, suicide mission if you will, because it's going to think, hey, I might be in a loop. Next, we're going to look at the packet type, and it identifies the upper layer protocols that are involved with this particular packet, like NCP, SPX, things of that sort that exist above the IPX layer. All right, here's the interesting part as well. We have destination address information. The network information, we expected that. This is a layer 3 unit. That's why it's called a packet. But then we also have the destination node or the node ID information right here. And this is why we have the ability within the routing protocols and the route tables when we look at them to represent these 2 units together because they exist in the same packet as they travel through the network. Then we also have a socket. Same thing happens on the source end. We have all 3 pieces of information again. And then the last thing we have here is an indication of the upper layer data that we're dealing with. So the design concept of not having specific media access control protocols set up for netware has its advantages because you can ride on those that are already existing, but it also has some things that you need to work around. One is this address information. The other is problems that arise when you're talking about encapsulation. Again, here's the model. I have a packet existing here at the network layer. As I want to traverse that packet down through my media access control, let's say out for Ethernet, then there's going to be certain naming conventions that are specific to the people that have set up these Ethernet framing types or encapsulation, right? Well, the problem is netware has one naming convention, Cisco has another, and it lends itself to some confusion. So that's what we want to clear up right here. Let's start off by discussing the types of frames we're dealing with. First, we're going to see here Ethernet with an IPX being encapsulated. Now, this Ethernet is labeled not as 802.3, but as Ethernet. And the reason for that, it's the original Ethernet, the one that had the type field. Remember the difference between original Ethernet and the 802.3 standard from IEEE is the fact that this had type, this had a length field. Okay, so that original format of the type field is what's supported here, and under the netware naming scheme, this is called Ethernet _2. And under Cisco, it's called ARPA. The reason for that is the original inception of the internet came from the ARPA group, so they named it ARPA. Now let's move on to the next. This is an 802.3 header, which includes the length field, but it doesn't have the standard 802.2 logical link control extension that you would see under a true definition of an Ethernet frame in 802.3 IEEE. So what they did is they left off this portion here, and the name for that under netware is now going to be Ethernet, again with the Ethernet, 802.3. And what they do is they simply name it this frame name based on what appears right before the encapsulated IPX packet. Okay, so 802.3 is the last thing you see, so it's Ethernet 802.3. Under Cisco naming convention, this is Novell dash Ether. All right, moving on to the next one. This is the standard or default IEEE 802.3 type of frame that you should see out there. And the naming convention under Novell is again with the Ethernet. Let me shorten it up a bit here. Ether, and the last portion of the packet it sees, which is 802.2. All right, under the Cisco naming convention, of course, it has to be a little different. We're talking about SAP for Service Advertisement Protocol. Not really. We're talking about the SAP field within this logical link control. All right, the next thing we have is a SNAP extension added to this standard frame. So we have 802.3, the 802.2 logical link control extension, and then SNAP. All right, and then the IPX packet that is encapsulated. So what we're going to have a name here is, I bet you can guess, the thing that appears right before the IPX, and that is Ethernet SNAP. All right, and then what we're going to have in the Cisco description is simply SNAP. At least these come close to matching, huh? I know these different naming conventions aren't easy to correlate, so you're just going to have to really commit them to memory. I will give you a bit of help, though, and I'll let you know what's supported under each of these frame types. Here we're going to support Ethernet, Ethernet here. Here it can be Ethernet, token ring, or FDDI, and the same, Ethernet, token ring, or FDDI for the last type of frame. Earlier within the IPX network command, we saw how we can change this encapsulation type. But what we haven't talked about is how we understand what encapsulation type is on an interface at the time that it's actually having an IPX network running on it successfully. So let's check that out. We're going to bring up router number 3 here. And what I'm going to do is issue the command show IPX interface E1/0. Now, it gave us the address before, so we're familiar with that part, but as I scroll up, let's see what else it gives us. It also tells us that we have the encapsulation type Novell-Ether working for us, which we identified here under the Cisco naming convention. For netware, that means Ethernet 802.3, and this is exactly what the frame would look like. Now, I want to change that. I want to change that to ARPA. And the reason I want to do that is we have a network that is working, an IPX network. I want to show you that when we have different encapsulation types on both ends of that network link, that our communication will no longer work. Now to do that, I have to set up a ping on router 1. So let's get into router 1. And what we're going to do is type in ping. This is the extended type of ping. Opt for IPX. And then the target IP address is what we need. I'm going to cut and paste that from router number 3. Let's copy. Paste. Before I hit enter, I want to get into the configuration mode of router number 3. So let me get through this command. Conf-T into the interface E1/0. All right, now I'm going to type in the command IPX network, just as we did before. Identify the network as ACE3, and then encapsulation. Let me hit the question mark. Here's where you see the 4 we looked at earlier: the ARPA, the Novell Ether, SAP, and SNAP. I'm going to change this to ARPA. We just saw that it's using Novell Ether at this time. So ARPA, hit enter. Before we go on with our ping, I'm also going to get ready the command to set it back to the original Novell Ether. I'm not going to initiate that until after the ping has started. What I'm going to do is I'm going to set up our ping, this repeat count that I'm looking at now. Instead of opting for 5, I'm going to opt for 30. That's going to give me 30 instances of pinging that device. All right, I'm going to hit the default there, the default for the timeout. Under verbose, I'm going to hit yes. At that point, it's going to start up, and you're going to see a series of failures. Let me get back up into router number 3. You can see the failures. There's 1, there's 2, there's 3. As soon as I change this encapsulation method back, you'll see successful tries. And here we go. Now it's set up to Novell Ether, and what did you see? Scroll back up here on router number 1. As soon as we made that change, 4 milliseconds, all the way through, even 1 millisecond at some point, up to the point that we have our successful ping. 76% were successful, everything 100% since we made the change on the encapsulation type. For the last section of this nugget, we're going to cover the Service Advertisement Protocol. Simply put, it's a way of servers on a network to advertise not only their name, but also the services they provide. So what's going to happen is N3 here, residing on this shared network environment as a server, is going to broadcast out Service Advertisement Protocol that is going to reach every device on this network. And in reaching that device, it's going to go ahead and read it and understand that N3 has a specific address, and at the same time offers a service. In this case, we're going to say it's a print server. So if anybody needs to print, come see me is what it's saying. Now, other servers and routers are going to store this information in a database. And what they're going to use that for is to direct the devices or the clients to those resources if they need them. Now, in the case of N1 and N2, they don't need to be directed there because they're on the same local area network or broadcast domain here. But if I have in existence another device, N5, on the other side of the router, that doesn't have these broadcasts reaching him for advertisement of the services that are happening on this end of the network, then the router is going to have to perform somewhat of a proxy. When N5 says, hey, I need to print, does anybody know where I can print? The router will say, yeah, I do. Provide the information. And then this device is able to go out here and print. Now, because that information contains both the logical and the physical addresses here in combination, I don't have to have the ARP process. Remember we talked earlier about half of the reason that we don't need ARP within NetWare, and that was the fact that these two addresses are contained together. Now, the other half is that it's a periodic update, that these SAFs are sent out, in this case, every 60 seconds, saying, hey, here's my name or my address, and this is what I do. If you need me, give me a call. In this nugget, we discovered that NetWare was developed by Novell Incorporated in the early 1980s. We also saw in a comparison between the OSI reference model and the NetWare model that the top 5 layers of the NetWare model were made specifically for that network operating system. And the bottom layers were just using the existing media access protocols. Then within addressing, we saw that IPX network addresses existed, and it's a combination of the network number, which is 32 bits, and the node ID, which is 48. Within the routing section, we saw that there was support for distance vector protocols in RIP, link state in NLSP, and also a balanced hybrid using the EIGRP protocol. We also saw that the RIP protocol was turned on automatically as soon as we issued the IPX routing command. Within encapsulation, we were able to clear up some naming convention problems that exist between Novell and the Cisco naming convention. And then we ended up by looking at the service advertisement protocol and its process. I hope this has been informative for you, and I'd like to thank you for viewing.